this talk, where we go to the picture of both varieties. And if I have a background in algebraic geometry, I will just directly jump into they can be realized in algebra geometric setting as follows. So we start with a quiver. Which looks like this. So we have basically the double of an type A quiver. And then we start considering a handsaw quiver like this.
So Tiziano, I thought you found something that said it was chainsaw. This is a handsaw. Handsaw and chainsaw are quite different. Your handsaw is a saw, and you go like this.
Yeah,
with your hand.
There are both of
Chainsaw.
these names.
Well, they have both of them.
In the easiest case, when you don't have the two-way part, it's handsaw.
Okay.
When you have also the stick,
Then it's a chainsaw, I see.
I think so.
Okay, so these operators will be called B.
Handsäge
Yeah,
und
absolutely.
Kettensäge.
Mhm. Yeah, sometimes writes that.
That's German.
Yeah,
Okay.
the German word and the English word really considered one by one, like hand is hand and Säge is saw. Okay, so each triangle of this form here gets a relation, namely we want that going this direction and takes the loop should be the same as taking the loop and going this direction. And the difference should be equal to going over this saw path. And then I also imposed stability conditions. Namely, if I have a subspace which is invariant under the B minus action, under the B plus action, and it is in the kernel of my operator A and in the kernel of the operator B, then this space vanishes. And also, if I have a subspace which is stable under the B plus action, and it contains the image of A and the image of B. No, it contains the image of the capital A and also the small a. Then I want that this guy equals the whole space. So these are stability conditions that can be phrased in the language of GIT. And it turns out that this thing is isomorphic to a moduli of NAM equation, which gives that actually these guys carry symplectic structures. So if I consider this variety, then locally every part as a Poisson bracket, and gluing together these Poisson brackets gives me a Poisson bracket on the whole variety, and this gives me a symplectic structure on the variety of quiver. The variety of quiver representations of this quiver where I impose these conditions. And another interesting fact is that this variety also turns out to be affine. So we get an affine, smooth, symplectic variety. Which also admits a moment map. Moment map with respect to the action of the general linear group corresponding to all of these spaces, but not these ones. So the moment map is explicitly given by we take a quiver representation. So this is right. Each of my arrows gets a matrix, and we demand that the A and B matrices satisfy this relation and these stability conditions. And then we map it to B0 minus B0 C0. So this is at this point here. And then would be minus B1, and then we move on with the next step and the next step here. Okay, and then the Bow variety is the corresponding Hamiltonian reduction, namely I take a certain GIT quotient with respect to the linear group action corresponding to these parts. Well, this variety comes with torus action, where each of my saw parts here gives me a torus vector, and there's also, as in the case of cotangent bundles of black varieties, a further torus action, which scales the symplectic form. And the family of Bow varieties contains the family of cotangent bundle of black varieties, and we are even more in the lucky situation that also the torus fixed point combinatorics naturally extends the torus fixed point combinatorics of cotangent bundles of black varieties. Namely, we have the following proposition due to Nakajima. Namely, the torus fixed points, where T is torus of rank n, which corresponds to all of these parts, they can be labeled by matrices which have entries in 0 and 1. We have a row sum condition, namely, if I sum up all elements in the ith row, then I get the difference between two of these spaces. And if I sum up all the columns, if I sum up the entries in one specific column, then I get the difference between two of these dimensions. And in the case where these guys here increase by 1 and then decrease by 1, this means then all these sums are just all these entries are equal to 1, which means that we have a matrix where the row sums are 1, the column sums are 1, all entries are in 0 and 1, so this is a permutation matrix. So yes.
What is M? What are M and N?
M is a matrix.
No, little m.
Where's little m? Little m is where this starts, this index here. And capital N is where this starts, ends. So we have, here we have, yes, the index of my input data. So here I have m vertices, and here I have n vertices. Okay, so yeah. So if I would have 3 here, then we would have 3 rows. And if I would have 4 here, I would have 4 columns. So this does not have to be a square matrix. And in the case where I have n guys here, n guys here, and the dimension goes up by 1 and then decreases by 1, this variety will turn out to be isomorphic to a flat variety. And these matrices will just be permutation matrices.
It's an element of C. It's an element of C. Not M.
Sorry, there's a bijection. Sorry. Yeah, the fixed points are classified by these.
Okay.
Yeah, by these things. Yeah, sorry. And so what is the one here? Is that fixed or converge? Could be both. So both are possible. We can so if we are type A, we can always push our curve to our goal variety to be of this presentation by doing Hanani different transitions.
It is a column branch. I think so. Yeah, in this case, with this configuration, should be a column branch.
So defining a column branch.
No, it can also be a quadrangular of back variety.
Yeah, I think there's a problem.
Are there always column branches?
You put a 0 there, right? Before of CDM.
Yeah.
So this one should be balanced.
No, they don't have to be balanced.
These don't have to be balanced.
Or because we got CDM.
They don't have to be balanced.
Okay. If D minus M is 0, it is balanced and from that.
So these guys can be balanced or co-balanced.
Yeah.
Okay. So let me come to the main result. And to formulate it, I need a little definition. Namely, that let's call this set S. So given a matrix in my set, then we say that another matrix in my set is obtained from my D by a simple move over R if there exists indices I0 smaller or equal than R, no, I0 smaller or equal than R, and IR is greater than R. Okay, I1. And also some J's, and I want that di0 J0 equals di1 J1 equal to 1. di0 J1 is equal to d J0 equal to 0. And then I want that my matrix D prime has the same entries, except at these positions here, where we swap the entries. So I want that D I0 J1 prime and D I1 J0 prime should be 1, and D I0 J0 D I1 J1 there, and D I J E prime IJ if the pair I comma J is not equal to the pair I0 comma J0 and all permutation of this. So I1 comma J1 I0 J1 and I1. So an example of this is that